This presentation is about the Andromeda galaxy. Now, the Andromeda galaxy is 2.5 million light years away, and it's moving towards the Milky Way galaxy at around 110 kilometers per second. The galaxies are expected to merge in around 4 billion years. But some contact between the outer dark matter halos will occur before that time. What is interesting is looking at that data about the position and movement of Andromeda is that we can project back in time and try to work out where it started. Just to illustrate the point, if you imagine looking out of a window and you see a ball passing by so that you can see the position and the velocity of that ball, you can work out the height from which it was dropped and the elapsed time. And we could use a similar principle because we know the position and velocity of Andromeda now, but we would like to know where it started and how long ago. Now, the problem is a bit more complicated than the example that I gave with the ball being dropped, because we have to take into account the expansion of space, which varies in proportion to x, the distance of separation between the Milky Way galaxy and Andromeda. And also the gravitational acceleration which acts on Andromeda is given by A equals gm over x squared, where x is the distance of separation and m is the mass of the Milky Way. So we have variation with both of these, so it's not a constant acceleration and it's not a constant recession velocity. So the approach I've taken is to use a spreadsheet to calculate the trajectory of Andromeda, and using the spreadsheet we divide the time into equal time steps, and I've listed below some of the constants which are used, and also showing how I've represented those constants in the spreadsheet. And I find it very convenient to have, for example, 1 light year, 9.46 times 10 to the 15. So I use 2 spreadsheet cells, one containing the number 0 to 10, and the next cell containing the power of 10. And I also keep a good track of the units because the gravitational constant G, measured in meters cubed, kilogram to the -1, second to the -2, means that all the other variables and constants have to be in meters, kilograms, and seconds. So the speed of light, 2.9979258 times 10 to the power 8 meters per second. 1 year, that's calculated simply by taking 365.25, multiplying it by 24 for the hours per day, and 3,600 for the number of seconds in an hour. 14 billion light years is a very convenient constant to have as a reference, because if you take a distance of separation and divide it by 14 billion light years and multiply by the speed of light, you get the recession velocity. So that's a very useful value to have at hand. We've taken the mass of the Milky Way, as 2 times 10 to the 42 kilograms. And the step size in time I've taken as 100 million years. And that might seem like a long time for an incremental step in a model. But you'll see when we come to use it that is justified. And in this case, the value turns out to be 315.576 times 10 to the power 13 seconds. And in the spreadsheet, we need to define some working variables. So x is the current distance of separation, and that will occupy 2 cells in adjacent columns. VE is the recession velocity due to the expansion of space. A is the current acceleration due to gravity, which is gm over x squared, and that would be in minus that because it's in the direction towards the Milky Way. And Vg is the accumulating velocity due to the gravitational acceleration. So here are the description of the first 2 rows of the spreadsheet. We start off with column X. Sorry, I shouldn't say column X, it's X, which is using the starting value of X. The column containing VE, we use the formula c times x over 14 billion light years, and that gives us the recession velocity. The next column, we get the acceleration, gm over x squared, and we represent Vg before the acceleration and Vg after. So this is before 1 step of time and after 1 step of time. So the difference between before and after is the acceleration times the step, which is a unit of time. That's actually 100 million years. Now we need to add the 2 velocities together to get a resultant recession velocity. And from that, we can calculate the increase in x, which is the velocity times the time for which that velocity applied. So having got the increase in x, we now can go to row 2 and add the increase in x back to our current value of x. So then we just complete row 2, and you can just drag down from row 1 into row 2, as long as all of the references to constants preserve row and column. Now I'm using numbers on Apple Mac. If you're using Excel spreadsheet, it's the $sign before the row and the column. So once you've completed row 2, all you have to do is to propagate that row down the spreadsheet for 1,000 rows. And what you find from this spreadsheet model is that from the starting point x, the distance of separation always increases due to the expansion of space, because the velocity Vg starts at 0, so you're always going to move away, and the effect of gravitational acceleration builds up. So whereas Ve has a linear relationship to the distance x, the gravitational velocity builds up over time due to the acceleration. And we're looking for a result that for a given starting point x, the galaxy passes a point at 2.5 million light years with an approaching velocity of 110 kilometers per second. And here's what we find by running the spreadsheet. So if you had a starting point X at 2 million light years, the furthest point of separation is at 2.373 million light years. In fact, that means it never reaches 2.5. So this result is not possible. For a starting point of 2.1 million light years, the furthest point reached is 2.6 million light years. So it does go beyond the known value of 2.5. And on returning, it gets to a point at 23.7 kilometers per second after 9.8 billion years. So you keep varying the starting value, and actually by a process of trial and error, you find that at 2.44 million light years, the furthest point reached is 4.967 million light years, and the speed on returning to 2.5 million light years is 109.9 kilometers per second. So this is very close to 110, which is what we're looking for. And that happens after 53.9 billion years. What you find is beyond 2.46 million light years, the Andromeda galaxy would never return, as the expansion of space always wins. It's never exceeded by the gravitational velocity, and the galaxies would continue to move apart indefinitely. So here is the table of results from the spreadsheet. You can see the calculation for various values starting from 2. So it's only quite a narrow range from 2.1 to 2.452, which produce results which could be applicable at all. And it's this column here, and you can then see that carrying on for a few more rows, you find that the distance of separation drops to 0 at 58.1 billion years, which is in 4.2 billion years time. So this seems consistent with projections that other people have made for the expected time of merger of Andromeda and the Milky Way galaxy. So what I'm going to do now is I'm going to stop sharing briefly just to pick up the spreadsheet and show that to you. So there's the spreadsheet. So you can see I've put some information in at the top just to describe what we're doing here, and the various constants that I've set up are 1 light year, the gravitational constant G, the mass of 2 × 10⁻42 kilograms, an expansion constant, which actually I don't use in the calculation because using this 14 billion light years does the trick in an easier way. Speed of light, 1 million light year, 14 billion light years, and this is the start point. So this is the value that in the spreadsheet that you change. So if I change this to 2.44, that should give us the value that that is the one that we're showing is the current is the correct conclusion. So I've I've put a constant which is the target that we're trying to recognize, which is 2.5 million light years, and that's expressing it in meters. And also the step length here is 100 million years, and that translates to 315.576 times 10 to the power 13 seconds. So here is the, and in the first column here, I've just put increasing numbers from 1 to 1,000, which denotes the step number. So this is the starting point, referencing back to cell C16, which is the start distance in meters. So now this is our expansion. Now you'll see in this case, I've multiplied the value by 1,000, and I've subtracted 3 from this value. And the reason for doing that is so that VE and VG are using the same power of 10, because we need to add them together later on. But this is basically x, the distance of separation, times the speed of light divided by 14 billion light years. So here we're working out the acceleration, and it's shown as negative. And this is minus gm over x squared. And the value is 10 to the minus 11. So you can see it's because of the huge distance of separation, the acceleration is very small. Vg before the acceleration always starts at 0 in the first row. And then after the acceleration, this is the acceleration before plus the step size times the acceleration. So you can see here a kind of justification for using such a apparently large step size, because the value of Vg compared to Ve is relatively small, and the increase in x that we get is 0.1 compared to the current value of 23. So we're talking about an incremental value of 1% or less. And again, we make sure that x has the same power of 10. The increase in x has the same power of 10. So this is just a marker to say is x greater than the target, and if it is greater than the target, so if x is greater than 2.5 million light years, then it's 1, otherwise it's 0. So you can see in the last column, I've just converted x back to millions of light years, and you can see fairly rapidly we move out to exceed 2.5 million light years. So having completed row 1, we just need to take row 2 as the row 1x, or the row 0x, plus the increase. And then all of the other rows we can just propagate down, except we have to make sure that our new VG before is equal to our VG after from the previous row. And once we've got row 2 set up, we propagate row 2 all the way to the bottom of the spreadsheet. So now we can examine the data, and we put in 2.44 as our starting point. So we're watching the last column here to see when we get to the maximum value. You can see it's still increasing, somewhere around here, 4.5, 4.6, 4.7, 4.8, 4.9, 4.96. So somewhere around here, we're reaching the maximum distance of separation. I think it's this one here. So that, if we then go over to our left-hand side, it's after around 33.8 billion years. And then we carry on till the ones go to 0, which is here. And then we look, this is the value here, which is our velocity of approach. And that happens at 53.9 billion years. So each of these steps is 100 million years. So 539 represents 53.9 billion years. So we could look at other possible. So what in sheet 2 I've just recorded with a different start distance. This gives you a different final result. So if we were to put 2.2 in here, and then run over to the right and down the spreadsheet, we find that it takes a while longer before we get up to 2.5. But at the point that the 1 turns to 0, which is here, that's when we're coming back. We find that the velocity, here we are, is 43.9 kilometers per second, and that's after 14.8 billion years. So that's the model. I think there's probably enough information for you to build the spreadsheet yourself, and you probably won't believe the answer unless you do build it yourself. But my conclusion from the model is that this observation that the Andromeda galaxy is moving towards us at 110 kilometers per second, while we're 2.5 million light years apart, that observation proves that the Big Bang theory can't be correct, because the elapsed time for that to happen is 53.9 billion years, which is well in excess of the value of 13.8 billion years, which is the supposed age of the universe.